Every click, every connection, every single packet of data, it all leaves a trail. But how do investigators actually follow these invisible breadcrumbs to uncover the truth in our digital world? Well, that's what we're going to get into, the fascinating field of network forensics.
And to really get a grip on how powerful this stuff is, you don't have to look far. I mean, remember that massive college admissions scandal a few years back? That case wasn't cracked by some dramatic confession in an interrogation room. Nope, it was unraveled piece by piece through digital evidence. The emails and the text messages, that was the smoking gun that exposed the entire scheme. It's a perfect example of just how critical network forensics is in any modern investigation.
So where does an investigation like that even begin? Well, it starts by treating the network itself as a crime scene, a digital landscape that's just full of potential clues, evidence, and hidden stories that are just waiting to be told. At its core, network forensics is exactly that. It's about applying scientific and investigative methods to analyze all the data that's being transmitted across a network. It's all about piecing together events from all these digital fragments to build a case that can actually stand up in court. Every device, every server, every single connection is a potential source of evidence.
Okay, so if the network is the crime scene, where are the fingerprints? Where do investigators look for those crucial pieces of evidence that connect a person to a digital action?
First up are DHCP servers. Now, think of a DHCP server as the super meticulous guest book for a network. Whenever a new device, a laptop, a phone, you name it, connects, this server automatically assigns it a unique network address, or IP address, and it makes a little note of it. And the forensic value of these logs is just immense. They record the IP address that was given out, the device's unique hardware signature, that's called a MAC address, and a really precise timestamp. This allows an investigator to definitively link a specific physical device to specific network activity at a specific time. It's basically the digital equivalent of placing a suspect at the scene of the crime. Next up, we've got firewalls. So if the DHCP server is the guestbook, the firewall is the network's security guard. It stands right at the gateway, inspecting all the traffic that's coming in and going out, and it makes decisions based on a really strict set of rules about what's allowed and what's not. A firewall creates this really critical barrier between the private, trusted internal network and the, well, wild and untrusted internet. And most importantly for us, it keeps a detailed log of everything it sees. That log is another treasure trove for investigators. They can see what traffic was allowed or, sometimes more tellingly, what was denied. They can see source and destination IP addresses, the specific ports used for communication, and uncover patterns that just scream foul play, like repeated attempts to access a secure server or huge, unusual transfer of data out of the network. Okay, so we know where the clues are, but there's a huge challenge here. How do you actually collect that data? See, it's not enough to know the evidence exists. You have to capture a perfect, unaltered copy of it as it flies by. One of the classic tools for this is called tcpdump. It's a command line utility that, in a nutshell, lets an investigator listen in on the network's conversation. It intercepts network traffic in real time and displays the raw data packets. Looking at this, you can see what that raw capture looks like. Now, to the untrained eye, it's just a jumble of numbers and text, right? But to a forensic analyst, this is the digital crime scene, frozen in time. Each line is a packet, a piece of the puzzle they can use to reconstruct exactly what happened. But this raises a really critical question. When the integrity of your evidence is everything, how do you guarantee you're capturing a perfect copy of every single packet? And how do you do it without the network or a potential suspect even knowing you're there? This brings us to a really fundamental choice in evidence collection, and it's a big one. On one hand, you have a network tap. This is a physical device that sits right on the network cable and creates a perfect bit-for-bit copy of everything that passes through. It's invisible and completely reliable. On the other hand, there's a span port. It's a software feature on a network switch that also copies traffic. But, and this is a big but, this switch prioritizes its main job of forwarding traffic. So if things get busy, it can actually drop packets from the copy. For forensics, dropped packets mean missing evidence. And in a legal setting, missing evidence can cast doubt on your entire investigation and could even get a crucial piece of data thrown out of court. And that all leads to this perfect summary from the experts at Gigamon. The golden rule for investigators is tap where you can and span where you must. When the integrity of the evidence is paramount and you need a 100% complete picture to withstand legal scrutiny, a tap is really the only way to go. All right, so now that we have a perfect copy of the data, what's next? You can't just dive in randomly.
Digital forensics requires a strict, repeatable process to make sure that the findings are accurate, complete, and most importantly, admissible in court.
This structured process is broken down into 6 distinct phases. It starts with identification, just figuring out what evidence might exist and where it is. Then comes collection, using tools like taps to gather it. Preservation is absolutely key. You have to make sure the original evidence is never altered. Then you have examination and analysis, where investigators dig through the data to find the relevant clues. And finally, there's presentation, where the findings are reported in a clear, concise way for a court or jury to understand.
It's also important to see that this forensic process doesn't happen in a vacuum. It's a critical component of a much larger framework, like the SANS incident response cycle you see here. This whole thing provides a comprehensive plan for handling security incidents, and forensics plays a key role in several of its stages, from containing the incident to eradicating the threat and learning lessons for the future.
We've talked about tools and we've talked about processes, but there is one single concept that underpins everything. It's what transforms raw data into legally sound evidence. It's the unbreakable chain.
So let's explore this crucial question. What exactly is a chain of custody? Because without it, all the technical work we've talked about could be for nothing.
The chain of custody is the meticulous, chronological documentation of an evidence item's entire life cycle. Think of it like the unbroken seal on a physical evidence bag. It proves that the digital file presented in court is the exact same one collected from the crime scene and that it hasn't been tampered with at any point.
A robust chain of custody has to answer all of these questions without any gaps. What exactly is the piece of evidence? How was it collected? Who has handled it? And when? Where has it been stored? And why was it ever moved or transferred? Every single one of these questions must have a documented, verifiable answer.
So this whole journey, from a single packet of data captured by a network tap to a piece of evidence shown to a jury, is held together by this meticulous process. The technology finds the clues, but it's the procedure, the chain of custody, that protects their integrity and gives them their power.
And that leaves us with a final thought. In a world where our lives create a constant, ever-growing stream of digital data, the line between just our personal information and potential evidence is blurring. So who ultimately holds the responsibility for protecting the integrity of that truth?